Good afternoon, ladies and gentlemen. My name is Vladimir Gureev. I'm a research fellow at Powolsky State University of Telecommunications and Informatics. Today I'm going to present to you our collaboration study on the simulation of data transmission in a simplex acousto-optical channel on a dual-mode optical fiber. Acousto-optical effect is put to good use in the various fiber optic devices of different application, such as conversion detectors, mode converters, filters and modulating equipment, different physical quantity sensors units and so on. The acoustic sound detection capability with the fiber optic sensor was demonstrated as early as in the late 1970s. Compared to a typical electronic microphone, fiber optic acoustic sensors have advantages of wide frequency passband, electromagnetic and radio frequency interference immunity, remote probing capability, direct connection to optical telecommunication network, and several others. There has been carried out a great number of studies facilitating the development of fiber optic acoustic sensors and technologies connected with them. These are the sensors on Fabry-Perot and Mach-Zehnder interferometers, fiber Bragg gratings, tunable laser sensors, and so on. However, multi-drop acoustic detection circuits on such sensors are limited in distributed probing realization feasibility. This problem is not met in the widespread during the recent 3 decades distributed fiber sensors based on backward radiation measuring in optical fiber. These sensor systems are exploited for the condition and safety control of extended objects in various spheres including transport, oil and gas sites, and technological process management systems. DAS market is on the rise and is expected to have passed the $2 billion mark by 2025. Alongside this, it should be noted that the realization of distributed fiber sensors based on the reflectometrical methods is pricey and requires implementing rather complicated layouts and devices. For a variety of applications, source localization on a distributed object is not required. It is enough to elicit its presence fact on a long span and to estimate parameters variations. It is sufficient to build a distributed acousto-optic fiber communication channel, vibroacoustic transmitter of which can be placed at any point on fiber length. Such distributed acousto-optic fiber channel may be used not only for vibroacoustic impact presence control and for estimating its parameters, but also for simplex audio communications organization from areas with high explosion danger or high levels of electromagnetic radiation. In such a case, the acoustic signal transmitted do not require direct connection to the certain point of the line cable. The same approach is also used for audio information retrieval. As a rule, such ways, as well as the reflectometrical ones, are based on the reception of very weak backscattered and reflected optical signals. To significantly raise the received signal level, there are ways based on the reception of optical emission spread forward in multimode optical fiber. There are well-known distributed acoustic sensors on multimode optical fibers, for which the target evaluations are got according to speckless analysis results. That requires the usage of high computing resources. At the same time, the acoustic sensors built on mode interaction products measurements at multimode optical fiber output are far easier in realization. The way of building the simplex acousto-optical communication channel on dual-mode optical fiber is the approach involvement. The proposed solution is based on the fact that dual-mode optical fiber is actually the Mach-Zehnder interferometer, which is successfully used for building acousto-optical modulators and sensors. However, this is the case for the first approximation. As a rule, the modes coupling percentage vary along the cable randomly, and the variations can be of periodic nature. While their dependence on vibroacoustic action is evidently seen in ultrasound frequency range, it can be ignored in the low frequency range of interest. We're assuming that an acousto-optical channel is aimed at low-speed signals transmission in audio spectrum and uses dual-mode optical fiber where the launched modes are sustained. In simulation, it is enough to consider the two modes, supposing that the orthogonally polarized modes degenerate. Each of the modes transmits a desired signal and crosstalk conditioned by the mode's interaction. As the desired signal is transmitted with the low speed, we can ignore chromatic dispersion and optical fiber nonlinearity. We restrict ourselves with analysis of one optical fiber cable length that makes an average of 4 to 6 kilometers, that allows us to exclude junctural irregularities and to ignore losses. We assign indexes 1 and 2 respectively to mode settings and to optical signals transmitted by them. In a routine optical fiber, the modes of azimuthal order number are not linked. although there is no ideal and the fiber optical cable length has irregularities. They can be divided into inner and junctural ones. The junctural ones appear in the optical fiber couplings. The inner irregularities are divided into interfibrous and intercable ones. The interfibrous irregularities are conditioned by parameter profile fluctuation of optical fiber refractive index and its core diameter. The intercable ones are generally caused by excessive fiber length in the cable that results in the fiber band. We will assume that the crosstalk level is considerably low, so that reverse crosstalk can be ignored, and for modes interaction description at an optical fiber signal local in frequency, we can adopt the following model, see equation 1. Then, at far end, the optical signals transmitted by the modes can be represented as follows, see equation 2. Subsequently, after a range of transformations, the sum of signals transmitted by two modes and arriving to the photoreceiver input far end can be generally represented as follows, see updated equation 2. Let us assume that the intermode link changes along fiber axis with the period L and the amplitude C, which, considering the taking communication model on the local irregularity, takes on a value from 0 to 0.5. Subsequently, we can see the result in equation 3. Applying equation 3 to equation 2 and using the known formula for cousin production performance by cousin sum, we arrive to standard integrals. As the signal comes to the square law receiver input, we take the square of the sum signal at far end considering the integrating results. We ignore up to the second order terms inclusively, d-embed low frequency component, and exclude the steady one. In addition, we assume that the propagation constant's variation due to the vibroacoustic action is proportional to its intensity. As a result that we get, the signal strength at filter output of the photoreceiver, including the desired signal and intermode crosstalk, can be written by the following approximation, see equation 4. As an example, there has been studied the fiber optic communication line including an optical fiber length with dual mode optical fibers. The optical fiber cable length is 5,000 meters. It was supposed that at the transmission line near end in optical fiber there were excited two modes, LP01 and LP11, by a coherent optical emission source. At far end of fiber optic transmission line, the both modes are transmitted to a square law detector, at the output of which, with the help of filters, the low frequency signal is selected and the constant component is rejected. There is vibroacoustic action done on the cable optic fiber of 10 meter section. The distance from the near end to the section beginning is 1000 meters. The differential model delay was set equal to 4.5 picoseconds per meter. The source of vibroacoustic action develops impulse-to-Scott chain with frequency of 1 kHz. The low-frequency signal at the output of the square law receiver was simulated using the described above model. Bit error rate was estimated implementing the Q-factor concept with allowance for the photoreceiver Gaussian noise. On the picture, there is shown an example of the bit error rate dependency upon imbalance of power between modes per unit value. For this very case, the infrequence change period was 10 times longer than the bit length of the dual-mode optical fiber modes under consideration, where the regularities amplitude was set equal to 10 in -6 per meter, 10 in -4 per meter, and 10 in -2 per meter. The action intensity was considered to be equal to 0.0005 rads per meter. The noise-to-signal ratio at the photoreceiver output was taken to be equal to 30 decibels. According to the calculations, the period and the amplitude of intermode link oscillations along the fiber do not substantially influence on the communication quality in the channel in question. There should be noted that the bit error rate drops to near zero with the balance of intermode links variation period and bit length between the modes. On the other hand, with this, the tuning out makes less than 10 in -10%. That does not permit to speak about this effect application. Link's expansibility at the local point requires its own studies. The model suggested in the work cannot be used for the goals as it has been found for low coupling conditions. The simulation results bring into sharp focus the dependence of transmission quality in the channel of interest and the imbalance of power between the modes. Thus, with the uniform input, the bit error rate is almost fully conditioned by the photoreceiver Gaussian noise. However, with the imbalance increase by more than 20 to 30%, there is felt the crosstalk considerable contribution. Consequently, the analysis of the results prompts us to suggest that otherwise things being equal, the bit error rate in considered simplex acousto-optical communication channel on dual-mode optical fiber can be significantly reduced, providing uniform mode generation at optical emission input into the fiber and limiting the imbalance of power between the modes. Thank you for your attention.